Download this code from codegive.com, link in the description below. Concurrency control without locks, a deep dive. Concurrency control is a crucial aspect of building robust and scalable multi-threaded applications. Traditional approaches often rely on locks, mutexes, semaphores, etc., to synchronize access to shared resources. However, locks can introduce significant challenges, including deadlocks when two or more threads are blocked indefinitely, waiting for each other to release locks. Priority inversion a high priority thread is blocked waiting for a lower priority thread to release a lock. Convoying threads queue up waiting for a lock, reducing overall throughput. Lock contention excessive competition for locks leads to performance degradation. Debugging complexity lock-related issues can be notoriously difficult to debug. Fortunately, there are alternative strategies for concurrency control that avoid explicit locks. These techniques, often grouped under the umbrella of lock-free or wait-free concurrency, can offer improved performance, scalability, and resilience in certain scenarios. This tutorial will delve into these lock-free techniques, explore their advantages and disadvantages, and provide code examples to illustrate their application. Fundamental concepts. Before we dive into specific techniques, let's clarify some key concepts. Atomic operations these are fundamental operations that are guaranteed to execute completely and indivisibly, even in the presence of other threads. Modern processors provide atomic instructions like compare and swap, fetch and add, and load link/store conditional. These instructions form the bedrock of lock-free algorithms. Memory barriers/fences compilers and processors often reorder instructions for optimization. Memory barriers, also called memory fences, are instructions that enforce specific ordering constraints on memory operations, ensuring that changes made by one thread are visible to other threads in the correct sequence. They're crucial for maintaining data consistency in multi-threaded environments. Lock-free versus wait-free lock-free at least one thread is guaranteed to make progress in a finite number of steps, regardless of what other threads do. Other threads might be starved or temporarily blocked. Wait-free every thread is guaranteed to make progress in a finite number of steps, regardless of what other threads do. Wait-free algorithms are more robust than lock-free algorithms but are generally more complex to implement. 2. Lock-free techniques and algorithms. Here are some common lock-free techniques with detailed explanations and code examples, primarily in C++ using atomic for demonstration. 1. Atomic variables The simplest form of lock-free concurrency involves using atomic variables. These variables provide atomic access to basic data types, integers, booleans, pointers, etc. Explanation std atomic int counter, 0, declares an atomic integer variable counter initialized to 0. Counter ++, the increment operation is atomic, meaning it's performed as a single, indivisible unit. There's no need for locks to protect the counter. Advantages simple and easy to use for basic operations. Avoids lock contention and deadlocks. Disadvantages limited to basic data types and simple operations. May not be suitable for more complex data structures. 2. Compare and swap, CA. CA is a fundamental building block for many lock-free algorithms. It atomically compares the current value of a memory location with an expected value. If they match, it replaces the current value with a new value. Otherwise, the operation fails, often returning false. Explanation asterisk. Asterisk value dot compare underscore exchange underscore week, expected, desired, this is the CA operation. It attempts to atomically compare the value of value with expected. If they match, it replaces the value of value with desired and returns true. If they don't match, it updates expected with the current value of value and returns false. Asterisk the while loop handles potential failures of the CA operation. If the CA fails, because another thread modified the value concurrently, the loop reloads the current value, calculates the new desired value, and tries the CA again. Advantages asterisk. Asterisk enables atomic updates to shared data without locks. Disadvantages asterisk. Asterisk can lead to ABA problem, explained later. Asterisk requires careful handling of CA failures, using retry loops. Asterisk can be more complex to implement than simple atomic operations. 3. Lock-free stack asterisk asterisk. Let's implement a lock-free stack using CA. This example demonstrates how to manage pointers atomically. Explanation asterisk. Asterisk std atomic node t asterisk head, head is an atomic pointer to the top of the stack. Asterisk push, t value. Asterisk creates a new node. Asterisk in a loop. Asterisk loads the current head pointer. Asterisk sets the next pointer of the new node to point to the old head. Asterisk uses CA to atomically update the head pointer to point to the new node. The CA operation ensures that no other thread has modified the head in the meantime. Asterisk pop, t end value. Asterisk in a loop. Asterisk loads the current head pointer. Asterisk if the stack is empty, head is null, returns false. Asterisk gets the next pointer from the current head. Asterisk uses CA to atomically update the head pointer to point to the next node. Asterisk if CA succeeds, retrieves the data from the popped node, deletes the node, and returns true. Memory ordering asterisk. Asterisk std memory underscore order underscore acquire, a load operation with acquire semantics ensures that any writes made by other threads before they release the same memory location become visible to the current thread. This prevents data races and ensures that the current thread sees consistent state. Asterisk std memory underscore order underscore release, a store operation with release semantics ensures that all writes made by the current thread before the store become visible to other threads that subsequently acquire the same memory location. Asterisk std memory underscore order underscore relaxed, this is the weakest memory ordering. It only guarantees atomicity of the operation itself, but it does not impose any ordering constraints with respect to other memory operations. It's generally used for the weaker compare underscore exchange underscore weak, which can spuriously fail, but it is important to use it in combination with acquire/release fences to guarantee atomicity of the overall operation. Advantages asterisk. Asterisk eliminates lock contention. Asterisk can improve performance in highly concurrent scenarios. Disadvantages asterisk. Asterisk more complex to implement than lock-based stacks. Asterisk requires careful memory management, using techniques like hazard pointers or memory reclamation to avoid memory leaks due to potential ABA problems. Asterisk can be susceptible to the ABA problem, see below. 4. The ABA problem asterisk asterisk. The ABA problem is a common issue in lock-free algorithms that use CA. It occurs when a value changes from A to B and then back to A between the time a thread reads the value and attempts to update it using CA. The CA operation will succeed because the value is still A, but the underlying state of the system may have changed in a way that invalidates the update. Example, simplified. One thread 1 reads the head of the stack, finding it points to node A. Thread 2 pops node A, then pops node B, and then pushes node A back onto the stack. Now the head of the stack points to a node A that is potentially different from the original node A. Thread 1 attempts to copy the head from its old node A to the new node it wants to push. The copy succeeds because the head currently points to a node A. But thread 1 is effectively corrupting the stack by pushing its node onto a potentially different A than it originally intended. Solutions to the ABA problem hazard pointers threads register hazard pointers that indicate which objects they are currently accessing. Before deleting an object, a garbage collector checks if any hazard pointers point to that object. If so, the object is not deleted until the hazard pointer is cleared. This prevents threads from accessing dangling pointers due to concurrent deletion. Reference counting keep track of how many references to an object exist. An object is deleted only when its reference count reaches 0. This helps avoid premature deletion. Epoch-based reclamation, EBR divide time into epochs. When a thread wants to reclaim memory, it waits until all other threads have advanced to a later epoch. This ensures that no threads are still using the memory being reclaimed. This is an efficient and scalable method. Tagged pointers combine the pointer with a version counter or timestamp. The copy operation then checks both the pointer and the version. If both match, the update succeeds. This ensures that the value being updated is actually the same value that was originally read. This is also known as a double-wide copy, and requires hardware support, or emulation. Example of hazard pointers, simplified. Explanation of hazard pointers in this example One hazard pointer manager a singleton class that manages a collection of hazard pointers. Each thread that needs to access potentially shared memory acquires a hazard pointer from the manager. To acquire a thread acquires a hazard pointer before accessing shared memory. 3. Protect before accessing the memory pointed to by old_head, the thread protects it by setting the hazard pointer to the value of old_head. This tells other threads that this memory location is currently in use. 4. Validation the thread checks if the head has changed since it was first read. This check is critical. If head has changed, it means another thread might have modified the stack, and the current thread needs to restart its operation. 5. Release after the thread is finished with the shared memory, it releases the hazard pointer by setting it to null. 6. Safe deletion the pop function checks if any other thread is still protecting the node, i.e., if any other hazard pointer still points to it. Only if no other thread is protecting the node is it safe to delete. Important this hazard pointer example is a simplified version for illustration. A robust hazard pointer implementation requires thread-safe mechanisms for adding and removing hazard pointers and careful synchronization to avoid race conditions. It also commonly integrates with a memory reclamation system for efficient memory management. 5. Read Copy Update, RCU. RCU is a synchronization mechanism particularly well suited for read-mostly scenarios. It allows multiple readers to access shared data concurrently without locks, while writers update the data by creating a copy, modifying the copy, and then atomically replacing the original data with the updated copy. Key ideas read side critical section readers enter a read side critical section. During this section, they can access shared data without any synchronization primitives. Update, copy and replace writers create a copy of the data, modify the copy, and then use an atomic operation, example ca, to replace the pointer to the original data with a pointer to the updated copy. Grace period after an update, there's a grace period during which readers might still be accessing the old version of the data. The writer must wait for the grace period to end before reclaiming the old version. The grace period guarantees that all readers who entered the read side critical section before the update have completed their reads. Example, simplified. Explanation asterisk. Asterisk data, represents the shared data. Asterisk RCU data, encapsulates the data and the RCU mechanism. Asterisk data, an atomic pointer to the current version of the data. Asterisk read, returns a pointer to the current data. In a true RCU implementation, this would be surrounded by RCU_read_lock, and RCU_read_unlock, or similar functions that denote the read side critical section. Asterisk update, creates a copy of the data, modifies the copy, and then atomically updates the data pointer. It then waits for a grace period before reclaiming the old data. Asterisk grace period, simplified in this example, the grace period is simply implemented with std this_thread sleep_for. A real RCU implementation requires a mechanism to track active readers and determine when all readers have completed their reads, example using callbacks or a per CPU quiescence counter. Advantages asterisk. Asterisk highly efficient for read-mostly scenarios. Asterisk readers do not require locks, minimizing contention. Disadvantages asterisk. Asterisk writers require copying the data, which can be expensive for large data structures. Asterisk requires a grace period mechanism to ensure that old data is not reclaimed prematurely. Asterisk more complex to implement than simple locking. 3. Considerations and best practices. Asterisk performance trade-offs. Asterisk lock-free techniques don't always guarantee better performance than lock-based approaches. The performance depends on factors such as contention level, data structure size, and the cost of atomic operations. Benchmark your code to determine which approach is most suitable for your specific use case. Asterisk memory management. Asterisk careful memory management is crucial to prevent memory leaks and dangling pointers. Consider using techniques like hazard pointers, epoch-based reclamation, or other memory reclamation schemes. Asterisk compiler and hardware support. Asterisk lock-free algorithms rely on atomic operations provided by the processor. Ensure that your compiler and hardware support the necessary atomic instructions and memory barriers. Asterisk complexity. Asterisk lock-free algorithms can be significantly more complex to implement and debug than lock-based approaches. Thorough testing and careful reasoning are essential. Asterisk ABO problem mitigation. Asterisk carefully analyze your algorithm for potential ABO problems and implement appropriate mitigation strategies. Asterisk choose the right tool. Asterisk not all data structures or algorithms benefit from lock-free implementations. For simple cases, atomic variables might suffice. For more complex cases, consider specialized lock-free data structures provided by libraries or frameworks. Asterisk memory ordering. Revisited correct memory ordering is essential for lock-free algorithms. Use std memory_order_acquire, std memory_order_release, std memory_order_consume, std memory_order_sec_cst, and std memory_order_relaxed appropriately to ensure data consistency and avoid race conditions. Std memory_order_sec_cst is the default, but it is the most expensive. Use weaker ordering where appropriate, but always ensure your code is correct. Asterisk use existing libraries. Asterisk before implementing lock-free algorithms from scratch, check if existing libraries provide suitable solutions. Libraries like Boost.lockfree or similar libraries provide pre-built, well-tested lock-free data structures. 4. When to use lock-free techniques. Lock-free techniques are most beneficial in the following situations. High contention when multiple threads frequently contend for access to shared resources, lock-free algorithms can offer better performance by avoiding lock contention. Read mostly scenarios. RCU is particularly well suited for applications where data is primarily read and infrequently updated. Real-time systems. Lock-free algorithms can provide more predictable execution times compared to lock-based approaches, which can be important in real-time systems. Fault tolerance. Lock-free algorithms can be more resilient to thread failures because they avoid deadlocks and other lock-related issues. Performance critical applications. When maximizing performance is paramount, lock-free techniques can be worth the additional complexity. Conclusion. Concurrency control without locks offers significant potential benefits in terms of performance, scalability, and resilience. However, it also introduces complexities that require careful consideration. By understanding the fundamental concepts, exploring different lock-free techniques, and applying best practices, you can leverage lock-free concurrency to build robust and efficient multi-threaded applications. Remember to benchmark your code thoroughly and choose the approach that is most appropriate for your specific needs. Always favor simpler solutions when they provide adequate performance. Lock-free programming is an advanced topic and requires a deep understanding of concurrency and memory models. Start with simpler approaches and only use lock-free techniques when necessary.